Okay, so non-linear analysis with GSA. First of all, let me run through a few basics. Um, Linear analysis is, well, what it says. The displacement strain relationships are linear. The stress strain relationships are linear, which is because both are valid if the displacements are small, and so equilibrium conditions are developed at the original non-deformed geometry. So, well, when it deforms, it doesn't deform very much. What this means is the end results are linear, low displacement linear, you double the load, you double the displacement, and load forces are linear, you double the load, you double the bending moments, shear forces, so on, that sort of thing. What this means is that you can combine the results, but and of course it's all based on the non-deformed geometry, but if you get large deformations or large strains, you're going to get inaccurate results. To get the accurate results, you need to go through a non-linear analysis where the stress-strain relationship is not linear, displacement-strain relationship is not linear, and you may have plastic properties, and plastic yielding of materials, and so on. Results. Because the results are not linear, this means if you double the load, the displacement may be more or less than double, and likewise the internal forces, and so on. End result, equilibrium is on the deformed configuration, deformed geometry. How the loads move through the structure can be important, and the analysis results are not combinable. More of that point later. So, nonlinear covers a variety of effects. First of all, we've got geometric nonlinear. So for a linear analysis, such as this cantilever here, the axial force, the applied force P is going to be equal to the reaction F, reaction V is going to be equal to Q, and the moment is going to be Q times the lever arm. When you go to non-linear analysis, you get large deflection on this column. The sum of the reactions is still going to equal the sum of the applied loads, but the individual values are going to be different depending on the angle of rotation and deflections and so on. What does this mean in practice? Well, let me open up GSA, and what I'll do is first of all I'll do a model which is a 3-pin beam, something which just will not work in a linear analysis. So 3 node points, select those, join them up, and for the endpoints I am going to make those fixed, but the beams themselves, this one here, let's modify that one so I can release that one in the bending, major axis bending at both ends, and the second one I'll just release it at the far end, because otherwise we'll be over releasing this node here. Speaking of that node, let's add in a node load, just a -1, just a -1 load, and so we can see we've got pin, pin, pin. This is an unstable section under linear analysis. Of course, if I just give it a section, some sort of example hollow section, we're ready to go. Hitting this analyze button will give us a linear analysis, and that will fail because, as I said, this is unstable. This is, as far as linear analysis is concerned, this is a mechanism. No good. So what instead we do, if we do a new analysis which is a non-linear static, again, just grab that low case, don't bother to magnify it, and you see it has found the results. And unlike previously where we had we've been with bending moments, this is being taken entirely in axial load. There may be tiny moments on there, but they are sort of rounding errors really, rather than the real thing. It's essentially this is now an axial load model. Take another extreme example. Rather than the beam, if I just delete one half off and just get rid of that spare node, we now have a pinned cantilever. If I rerun this analysis now, look at the deflected shape. You see, magnification 1. This mechanism has now swung down. It's now hanging straight down. This is now in equilibrium at the deformed position, not the original position, but as you can see, the deformed position is quite a long way from the original. If we look at a slightly more complicated example, such as the column I showed in the PowerPoint, so let's just make it 10 meters tall, and so fixed base, and at the top there, which will be node 2. Let me just add in some loads. So -1 vertically, so axial load, and a horizontal load, which these will combine together to show us. GSA takes these two vectors because they're in the same load case, but if I make that load case 2, you see we've got vertical load and horizontal load, and they vector together to make the one. Let's give it a section. Now this is 10 meters. Ooh, no, wrong button. This button. I'll just give it a large section, square hollow section. That looks okay. And if we do a linear analysis on this, and then I add in a non-linear analysis, which I will give the name nonlinear. And the end results of these, well, if I switch off the collection shape moment, bending moment, shear force, axial. So the linear, which is this one here, we can see that the bending moment is 10, the axial is 1, the shear force is 1. It's all what we would expect, and the non-linear, very, very similar. Now if we boost these loads by, let's say, a factor of 1,000, we'll just rename this one so it's linear, be easier to read. Okay, we have results. So the non-linear, linear is still giving factors results. The non-linear, the results now are looking quite different. And the reason for this is deflected shape. Is deflection. This is a one-to-one magnification on the deflection. So it's moving quite a long way from the original. And if we look in the output as well, actually let's go to the output wizard. So the nodal displacement and the beam springs, just the table. We can see that, for example, the non-linear analysis, we're getting quite a large vertical deflection, as well as quite a large horizontal deflection on that top node, and we see the axial load is reduced, the shear force is increased and the moment is increased on the non-linear, because basically it's moving so far away from the original that the linear analysis just is not going to give the right answers anymore. Now we also have non-linear elements in GSA. All the GSA versions out there have the strut, tie and cable elements. Some will have the fabric elements. Now the strut, tie and cable, these are all one-dimensional elements. Strut, compression only, tie, tension only, cable, tension only, but a special tension only in that it forms a chain of elements where the nodes along the chain are not actually fixed in position, which can produce some quite interesting results. Fabric is, as you might imagine, a tension only two-dimensional element used for fabric structures. So non-linear elements, if I close that one and open up my non-linear elements model. Now in this model here I've got 3 bays. The first bay has got bars, so axial only. Second bay, ties. Third bay, struts. You'll see there a slight difference in colour between the two to help you recognise them. Now if we analyse this, and this is non-linear elements, but we're analysing with a linear analysis. The end result is the head shape, as you'd expect. But if we look at the axial loads, we can see that with the bars, both are under load at compression and tension. The ties, only one's under load. With the struts, again, only one is under load. Now these are non-linear elements in that when it runs the analysis, it's iterative. GSA will determine which tie is in compression, switch it off, which strut is in tension, switch it off, and then rerun the analysis. It's possible that the analysis might oscillate between two states and therefore not converge. So it's something to watch out for. Not too often, but can happen. Now I mentioned cable elements as well. Now cable elements. Now this model here, simple little model. Two elements, 2 pin supports, a tension load down here. Now if I just modify these to being ties and then run the analysis, you will note that the axial load is on this element only. The resolved reaction is equal and opposite. And you see, yeah, so the applied load, tension in that tie, and reaction force up there, and because loads are in line with that tie, there's no general deflection on that. Now if we change these ties to cables, and then rerun that analysis, the results we get are rather different. You see now this 20 kilonewton tension load has gone up this cable, round the corner, round this essentially a pulley, and then down the next one. So you get reaction of 20 there, and a much larger reaction at that point there. This can be very useful in GSA, but if it's misused, can produce some very strange results. So very powerful, but use with caution. We also have fabric elements, not available to everybody, but if I just put in some fabric properties in here, let me just use that to create the grid. And the thing about fabric is that it requires a fabric material. Now fabric materials are available if you switch on your preferences. And you have as different warp and weft or local X and local Y stiffnesses. So my 2D elements, I'm going to set these up as fabrics. Oops. Didn't want that one. And I will pin both the corners and the mid sides. Now normally with fabrics you have double curvature and pre-stresses to attain some sort of stiffness, but in this case I'm not going to. And let's create a 2D face load, just a simple -1 load on that. So we're ready to go for the analysis. I do a new analysis which is a non-linear. Default loads. Don't bother magnifying. It's going to move quite enough as it is. Remembered everything. And there we have the deflected shape. Now this looks quite symmetrical. Leave those on. Let's look at the displacement. And you see, yeah, it's reasonably symmetrical. Not entirely symmetrical, but in the main. But if I change the contour results to the reaction forces, you'll notice we're actually getting far more reactions at these points than these points, even though the structure is symmetrical. Now, talking about material non-linearity, in the real world, we're dealing with elements like materials like steel and concrete and so on. You get a stress strain curve which looks something like this. Now in the GSA analysis we actually simplify the bits and we just have a single linear stress strain, a yield point, and then a plastic deformation. This enables the end effect of this in GSA. If I go to model I created earlier, now this is a 2-span beam with a UDL on. Now in this I have defined a plastic steel property, so it has a yield value in there. I've also set up a linear and non-linear analysis. So let's run this. We see in the report there, on the non-linear analysis, we're getting messages that the section has been yielding and bending, so the stresses have come greater than the 275 capacity. The end results, I've got the linear bending moments. You see the linear elastic high hogging moments. The non-linear, the sagging hogging look pretty much the same, and we can check this maybe by calling up the contours and just set the magnitude. And yes, you can see the hogging and sagging moments are the same. The section has yielded, got plastic hinges at the support and the mid spans as well. Whereas linear, as we expect. Now talk about materials. If I just flip back to the this 2D element model, something in the latest version of GSA is orthotropic materials throughout. So what we can now do is I can define, so let's say a timber elastic orthotropic material. If I give this some typical values, so C20 material, density not a lot, and shear modulus should be less than steel, of course, and make sure that this 2D element is defined as a flat shell. And just run a linear analysis on those shells. You can see once again the reactions are going more to these points than these, because this is following the stiffness of the section. But if we look in deformation instead. Not deformation. Rescale. You can see, if you look at the deformation structure, this is very much now a one-way spanning slab, even though the structure itself is actually symmetrical. With nonlinear, we can also do buckling checks. Now, in GSA, we have both linear buckling and non-linear buckling, which and nonlinear can include the effects of plastic yielding, such as we saw just now. For the linear buckling, this is the modal or eigenvalue buckling, and like all linear analysis, the equilibrium is in any of the deformed positions. So the deflection is not the important thing, it's the load factor that it's calculating. And what GSA will do is actually give you a normalized deflection to 1 meter. So don't worry about what. So the deflection value is not important for linear analysis, whereas for non-linear, it's all been worked on the deformed geometry, and so the deflection is actually the correct one, and cannot take the plasticity into account. Now, the result on this is that, well, for low displacement graph, for a linear buckling, you've got a given load, and the deflection could be anything. For elastic non-linear, as you increase the load, it will gradually approach, possibly reach, but they come close to the linear buckling analysis. Whereas if you've got plastic material properties taken into account, the buckling load can be a lot less than the linear buckling load. So, example of this, if I close these models, and let's open up the column buckling. Now this model, as I said before, I have a 1 kilonewton load at the top, pin supports, no releases, and you can see we've got minor axis support on this column, so it is twice as long in the major axis as it is in the minor axis in this case. Now I've set up already both the modal and the member buckling. So let's look at the modal buckling. So the modal is the linear buckling check. I'll just take the first 4 and analyse this. Now because I've applied a 1 kilonewton load, the end result on this, the load factor, will essentially be the column capacity. And we can see there's the major axis buckle. Next mode, minor axis buckle. This time we're getting a load factor of 819, previous one 642, and of course you get the higher modes as well, 1500, 1900. Reality, of course, is the first mode will be the one which buckles first. Now, remember this 642 for the linear buckling. If we do the second buckling check, which is the non-linear member buckling, I'm asked it to look at these 4 elements here. Get the numbers for that. Again, the single kilonewton load, and this time it increments the loads until failure. So let's run through those. And you see the note at the end, it says that examine the axial force deflection curve to get the buckling load capacity. Now what this means is, if I just scale up, there's our deflection, which will be similar, see a similar shape to the modal. If we go to our chart views, non-linear analysis, just enlarge it a bit, we'll see as the axial force increases, to begin with, the deflection at the midpoint is reasonably linear, and then it starts to go and finally and this value here is actually about 630 kilonewtons, which is just 10 less than the linear elastic calculation. Now we can also do snap-throughs and similar calculations with this. If I open up this model here, which I prepared earlier, this is an arch with an asymmetric load on it, and in the analysis task, this is non-linear static. I've got automatic load increments set up, so what this will do is gradually increase the load. I've also got a displacement control, which is the middle node. This is a meter rise on this arch. And they're saying if this middle node moves more than a meter, stop the analysis. If I run this, don't need magnification, and it'll gradually increase the load until you can see the deflection value there. It has snapped through. See, there's application 1, and if we then look at the chart view for this, we can see that as the load factor, wait a minute, yes, let me just rerun that, adjusting this back down to 1, thank you very much. I'll give us a better graph. Right. Okay. View the graph. That's better. You see that the graph, deflection in the middle point, and you can see that where the deflection is snapped through, it snaps through the value of about 4.3 times the applied load. So you could view it as a factor of safety of 4.3 for that particular load, asymmetric load case. Obviously you need to run a few. I mentioned earlier as well that with non-linear analysis you can't combine the results together. Now what this means is, well, with in GSA you always apply loads in load cases, and then you analyse these loads, and you can include factors on these. You can have multiple load cases in your analysis case, and then you can combine these together in various ways. If it's linear, you can apply factors, but you can always put an envelope over the results to get the worst values. In more tabular form, load cases, dead load, live load, win load. Analysis cases, if you just hit the analyse all button, by default that will give you one analysis case per load case, and then you can combine these by factoring them and so on, and then the envelope case. So this is perfectly legitimate for a linear analysis. For non-linear analysis, on the other hand, again, whilst the load case is the same, the analysis cases, you have to do the combinations within the analysis case, and then the combination case is only really going to be the envelopes. Now how does it work? GSA uses a method called dynamic relaxation for the non-linear analysis, or GS relax. You might have heard it called, which is the name of the solver within GSA for non-linear. And it uses a dynamic relaxation method in that if we take our 3-pin beam we looked at earlier, and we apply a load, that load will accelerate the midpoint of that beam, and it will then reach a maximum point where the speed drops to 0, acceleration to maximum, and it will then oscillate or vibrate back and forwards between these out of balance positions. What we're looking for is equilibrium position, where, as it happens, the speed is at the maximum, but the acceleration is at 0, and also the kinetic energy is at the peak. And the kinetic energy is related to some of the damping, which I'll go into. So the damping because it was just oscillate backwards and forwards, we need to apply damping. Now, GSA has two types of damping in there. Viscous damping, which applies a resistance based on the speed or the velocity that the nodes are moving at. Or kinetic damping, which says, well, the point where the kinetic energy is maximum is going to be the equilibrium position. Therefore, if we estimate where the equilibrium position is, adjust the model to that, and then apply the loads again, it should converge likewise. It's good. Originally designed for 1 degree freedom structures, does actually work for the more complicated three-dimensional structures as well. Effects of the damping, as I said, if there's no damping at all, the deflections will just oscillate backwards and forwards forever. If we have some damping and the damping is just smaller than critical, it will overshoot the equilibrium and then come back and converge. But if we have too much damping, then it will take longer to converge. We'll get there eventually. So ideally speaking, you need just the critical damping, but of course that's difficult to judge. GSA will automatically be applying damping during the analysis, but if necessary you can go in and take manual control on that. Right. So some case studies, areas where the GSA non-linear analysis has been used. Just about all of these have won awards. Beijing Olympics water cube. This is in particular the ETFE foil pillows, which of course inflated, yielding and some quite double curvature surfaces. Other end of the scale, from the Museum of Modern Art in New York, this mylar fabric and cable structure, which was part of an exhibition there a couple of years ago. Stadiums, Khalifa Stadium in the Middle East, cables and fabrics, and supporting the arch as well. Or in Australia, the Melbourne Cricket Ground. So good cable structures, and of course you can see that those flying struts supported purely by the cables, and vice versa. Singapore Flyer, this Ferris wheel in Singapore, and in Washington, the Air Force Memorial, a steel and concrete composite structure. It's about 200 meters tall. It's got a fair size. National Assembly for Wales, building in Cardiff Bay for the government there. Or in Toronto, the Royal Ontario Museum. Interesting piece of deconstructionism. Footbridges. This is a 10 segmentary grid structure in Sydney, Australia. It does work, but the structural mechanism is quite cleverly hidden amongst all those cables. And there's another example, the Infinity Footbridge, the longest footbridge in Britain, which is also winner of the Institute of Structural Engineers Award last year for supreme engineering.